Hi, my name is Ethan, and today I'm going to talk about the method of polar coordinates and rotating frames. I will go into a summary of each as well as a derivation, and in the next few videos we'll use examples to show you how to use these methods. I'm going to start with a problem that's just in the fixed frame using the x and y coordinates to give a good baseline for the following derivations. So to start off, you have your frame right here. It's your I hat, this is j hat, it's your origin, O, this is a fixed frame. You have a point P, you measure P with the x coordinate, the y coordinate. So this is next I will show the kinematics of a fixed frame using the x and y coordinates. All right. So to start off with, you have r of p with respect to O equals, using the x and y coordinates, x I hat plus y j hat. Then you take the derivative of this with respect to time, and you have v of p with respect to the fixed frame equals x dot I hat plus y dot j hat. Next you'll take the derivative of this with respect to time, and you'll get acceleration of p with respect to the fixed frame equals x double dot I hat plus y double dot j hat. So this is simple enough. Next I will show the kinematics for a fixed frame problem, but the coordinate system will instead be r and theta. So in this part, I want to make it very clear that this is not the method of polar coordinates. It is just a fixed frame with a different coordinate system, where the frame itself is not rotating or moving. It's still fixed. So you still have the same I hat, j hat, fixed frame origin, points here. Only now when you measure the point, you have r here and you have theta here. So next I will show the kinematics for the r and theta coordinate system. So you have r of p with respect to O equals, using some basic trigonometry, you can see that this is going to be r cosine theta I hat plus r sine theta j hat. Then take the derivative of this with respect to time, but you need to remember that this is r is changing, theta is changing. I hat and j hat are not changing yet, so it's just a product rule of these two right now. So you have v of p with respect to with respect to the fixed frame equals r, this is a product rule, r dot cosine theta plus, use the chain rule because you're taking the derivative with respect to time and not with respect to theta, so plus r theta dot, this will be a minus r theta dot sine theta I hat plus another product rule, r dot sine theta plus r theta dot cosine theta j hat. So that's the velocity of p with respect to the fixed frame. And then next, we will take the time derivative of this, and you'll get the acceleration of p with respect to the fixed frame in the r and theta coordinates. So acceleration of p with respect to the fixed frame equals, derivative of this is r double dot cosine theta minus r dot theta dot sine theta. Now we'll move on to this. You have minus r dot theta dot sine theta minus r theta double dot sine theta minus r theta dot squared cosine theta times I hat. And then next I will take the derivative of the j hat part. So plus, it's another product rule. It's a r double dot sine theta plus r dot theta dot cosine theta. Now we'll move on to this part, another product rule, plus r dot theta dot cosine theta plus r theta double dot cosine theta minus r theta dot squared sine theta j hat. So this is the kinematics for our theta coordinates for a fixed frame problem. In the next video, I will talk about how to use the method of polar coordinates where the frame itself will start rotating and things will get a little bit more interesting. Also, you can simplify this for the sake of the video. I think most people can already simplify this by themselves, so I will leave that to you.